Dear students, we have already discussed Mendeleev's periodic table, which was based on Mendeleev's periodic law, which states that the physical and chemical properties are a periodic function of atomic masses, which means that when we arrange these elements in the increasing order of atomic masses, the elements with similar properties are repeated after certain intervals. We get a table by such arrangement, which is called Mendeleev's periodic table, and we have found that there were many defects in that table. For example, position of hydrogen was not clear, the position of isotopes was not there, similar elements were separated and dissimilar were put together, there were anomalous pairs of elements, cause of periodicity was not given, and position of lanthanides and actinides was not given there. So after that there came the a modern periodic law, which was given by Mosley in 1913. He found that the properties of elements are essentially depend upon atomic numbers and not atomic masses. That is, he said that the essential property of elements is atomic number and not atomic mass. And he put forth his famous law called modern periodic law, which states that the physical and chemical properties of elements are a periodic function of their atomic masses. It means that when we arrange these elements in the increasing order of atomic mass, atomic numbers, the elements with similar physical and chemical properties are repeated after regular intervals. And when he did so, he arranged them, we get a table of these elements, which is called a modern periodic table, and it is also called a long form periodic table. Let us discuss the structural features of this modern periodic table. When we arrange these elements, we get here, we like this, we get vertical columns. These are arranged in hydrogen, then we have helium, then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, and then we have here aluminum, silicon, phosphorus, sulfur, chlorine, argon, and potassium. And in this way, these are increasing order of these these atomic numbers of elements. And we get here, you can see that we have horizontal rows formed, and we have vertical rows here also. So this table is called a modern periodic table, and these vertical rows are called groups or families. This is one family, one group, one group, one group, and these are called periods. So we have two structural features of this modern periodic table. We have vertical columns, which are called groups, and horizontal, which are called periods. These are numbered from one. The groups, let us discuss first groups. Groups are, there are 18 vertical columns. These are called 18 groups, and they are numbered by 1 2. These are numbered, designated by 1 here. 1 2 3 4 5 6 7 8 9 10 up to 18. Okay, from 1 to 18 they are uh, designated by these numerals. So these, there are 18 groups. The groups 1 2, here we have group 1 2, and then we have 13 14 15 16 17 18. These are called representative or normal elements. The electronic configuration of this first is this is 1s1. It means all the elements of first group have lost this valence shell configuration is ns1. Then we have second group there, which has ns2. Similarly, we have 13 here. 13 group has ns2 np1. 13 14 has ns2 np2. Then we have ns2 np3 np4 np5 up to np6 is in 18th group. The 18th group has complete shell and are called, and do not take part in chemical reactions, or non-reactive. They are called noble elements or noble gases. Okay, the elements of group 13 to 12, these have configuration. The last electron goes to d subshell, penultimate d subshell, that is last but one shell. They have, in last shell they have s0 to 1. Some elements have vacant s subshell of last shell, or some have one electron. But the penultimate shell has n minus 1. That is, penultimate has d from 1 to 18. In group 13 we have D1, then we have 14, we have D2, D3, D4. Here we have D1, here we have D2, D3, D4, D5, D6, D7, D8 and D10. So all these d orbitals, we can accommodate 10 electrons are filled from this group third to group 12. These are called transition elements because there is transition of properties from highly reactive metals, these are metals, to non-metals. So here we have non-metals and here we have metals, and there is transition, there is change in properties from metallic to non-metallic character. Therefore they are called transition elements. Okay, so these groups, and then we have 18 elements, 18 no 14 elements after lanthanum. Here we have lanthanum. Lanthanum has atomic number 57 in group third, 1 2 3 group third. These elements following lanthanum are called lanthanides. Similarly, we have group 4, we have actinium. Actinium, the elements following actinium. Actinium has the atomic number 89. After 81, we have 90, 91, 93. These 14 elements are called actinides. These are placed separately here at the bottom of the table. These are lanthanides and these are actinides. Their configuration is ns2 n minus 1 d0 to 2, some have 0, some have 1, some have 2 electrons. Similarly, the f subshell of third inner shell has n minus 2, we call it, has 1 to 18 electrons. It means these are systematically filled from 1, f1, f2, f3, f4, f5. That means that f contains 7 orbitals which can accommodate 14 electrons, and these are systematically filled from this after this lanthanum. These are filled regularly, and in this in actinides after actinium, these are filled regularly, these electrons, and these are also called f block elements because the last electron goes to f subshell. These are this is the description of groups, the vertical columns. Then we have periods. Periods are horizontal rows. We have row 1, row 2, row 2. These are all also designated by 1 2 3 4 5 6 7 by these numerals. So we have 7 horizontal rows or 7 periods. The specialty of them is that in each period one shell is completed. First shell is completed in first shell, hydrogen and helium. You know that it can accommodate only, it has only one orbital, and that is filled 1 here, 2 electrons. Similarly, then we have second shell is filled in second orbital, lithium, beryllium, boron, carbon, etc. Third is filled from sodium. Similarly, we have fourth shell is filled in fourth period, and fifth shell in fifth, and so on. So one shell is filled in each period, and we have how many periods? We have 7 periods. The first period, first element, it starts from here. First of each is an alkali metal, and last of each period is a noble gas. You can see here sodium is an alkali metal of third period, and its last is argon, which is a noble gas. Similarly, potassium is the first element of fourth period, and it is an alkali metal, and last of it is krypton, which is a noble gas. So you should remember that each element of every period starts from an alkali metal and ends at a noble gas. There is another classification of these periods: 1 2 and 3. First 1 2 and 3, these are called short periods because first it contains only 2 elements, second and third contain 8 elements each. These are called short periods. Then we have fourth and fifth. These are called long periods because they contain 18 elements. You can count here 1 2 3 4 5 6 7 8 9 10 up to 18 in this one. So fourth and fifth contains 18 elements. They are called long periods. The sixth, the longest period, it contains 32 elements. These include these lanthanides also. These lanthanides are included in group 6. These are kept below in order to prevent the sidewise expansion, undue expansion of the periodic table. They are kept at the bottom. So basically these lanthanides, actides are basically included in group 6 and group 7. So group 6 is called longest period because it contains, including lanthanide, it contains 32 elements. Then we have group 7, it includes actinides, and it is called incomplete period sometimes because all the elements of this do not exist naturally. they were later on discovered and this synthesizer. So this was all called incomplete sometimes, today we know the properties of all these elements. Okay, then we should discuss it as other features of this in this video second. Okay.